Hi, this lecture is meant to introduce you to the concept of capacitance. So the way I'll start is I'll say that the simplest possible capacitor is two pieces of metal that are separated by what is known as the vacuum, right? So the vacuum is empty space. So here's the situation. So here's one piece of metal, and here is another piece of metal. Notice that I wasn't particularly careful about their shapes, and I'm not particularly careful about how they're arranged. So for example, they could be arranged with, a certain distance between them, and I could have put this box oriented a different way. Or I could have oriented the other sort of like amorphous thing into a different shape, right? But those details are pretty important. But if I just want to think of, or introduce myself to the idea of capacitance, I only need to start with two pieces of metal. I'll organize how they're oriented and how far apart they are. And I know that what separates them is the vacuum. And this is a capacitor. And that's all you need. So what you can do, though, is explore the capacitance. And what this means is the following, right? So let me put a colon. So exploring the capacitance, the way you do this is you think of these two pieces of metal as actually being electrically neutral. So I say that for example, the conductor on the right-hand side doesn't have any charge, and the conductor on the left-hand side also doesn't have any charge yet. And what I'm going to do is, in order to explore the capacitance, I'm going to change the charges, but I'm going to do it in a particular way. The particular way that I'm going to imagine the electric charge of these things is to imagine it separated. So I'm going to separate the charge little q. And what this means, so let me take, so our two conductors, I'm just going to copy it and paste it down here. Okay, so if I separate the charge q, what this means is I'm going to grab this charge q maybe from the right-hand side. So if I take the charge q from the right-hand side, the right-hand side's charge becomes negative q because I took q away from 0. But I'm going to take that charge that I removed from the right-hand side and put it on the left-hand side. And so this is what's meant by separating the charge. And capacitance is about separated charge. So what happens, though, is if you think about it, before there was any charge, there was no electric field anywhere, right? Because these two things are uncharged, there's not going to be any electric field throughout the space between these conductors. But once you separate the charge, there's definitely going to be electric field. The electric field is not 0. And if the electric field is not 0, then that means that there is a potential difference that is also not 0. Up here, with the electric field being 0, if you calculate the potential difference, you're only ever going to calculate 0, right? Remember that the potential difference is negative the integral of E dotted over, actually let me use the symbols we've been using, dotted over some way to displace, right? So the potential difference that I'm talking about is the potential difference from, say, this place to this place, right? And so I'm going to imagine doing this integral from here up to there, or something like that, right? So I'll integrate up a potential difference, but because the electric field is zero, this is just going to integrate to zero. But because the electric field is no longer zero, if I manage to separate charge, then the potential difference is no longer zero. But what's interesting, here's an interesting fact, and this is an important, interesting fact, actually. And it's something that you can use in the future. So it starts off by saying, if you were able to double the charge absolutely everywhere, what you will get is the electric field everywhere will also double, and the potential difference between any two places in space will also double, right? So it's simply saying that there's a proportionality. If you were to imagine, so there's an electric field in the space between these two conductors, right? But instead of just separating little q, what if I separated twice q? Then the doubled charge separation would lead to a doubled electric field everywhere. It's kind of like I separated the charge q and got E, and then if I separated the charge q again, I would get another E, and the net electric field would be twice E. And if the electric field doubles, then the potential difference that you calculate will also double, right? That's simply this. Okay, so separate, charge Q get delta V, right? That's what we just did. We separated a charge Q. We understand that we get a potential difference, and we can define the capacitance right now. The idea is the capacitance is simply the ratio of the charge to the potential difference. So this is the definition of capacitance. And so the title of this lecture is Introduction to Capacitance and the Farad. So what's the Farad? So remember that units, right? In particular, let's study international system units. The units that we use for the charge are coulomb. So that's another C, but you have to judge from context. This C right here that describes the units of a charge, you should remember that that's referring to coulombs. But this right here, which is the ratio of the charge separated to the associated potential difference, that's called the capacitance. It's also labeled by a capital C. The delta V is the volt, right? That's the SI unit. I often put the unit with these little serif capital V's. So whenever you calculate capacitance as Q per delta V, the unit is going to be coulombs per volt, right? That's what the unit is. And 1 coulomb per 1 volt is called the farad, which is the unit of capacitance. So the farad is the SI unit of capacitance. So typical realistic circuit capacitors so like in electronics, so I'll put in electronics, tend to have microfarads or nanofarads or even picofarads. That is, 1 farad is a huge capacitance. Okay, so one last thing is, remember that our capacitors are just 2 pieces of metal, right? So here's a piece of metal and here is another piece of metal. And this capacitor, I could call it capacitor A, is in general going to have a different capacitance than this capacitor. For example, let's take a really, really big flat sheet of metal and separate it by a small distance from another big flat sheet of metal, right? So these are both pieces of metal with some thickness, but we imagine them to be quite thin. And these 2 pieces of metal have a certain distance of separation between them, and each of them has an area A. And this arrangement of these 2 pieces of metal is called a parallel plate capacitor, or parallel plate cap. The cool kids say cap for capacitor. There's many other arrangements. You could have 1 plate and a sphere. This is a different capacitor than the parallel plate capacitor. I don't know what this one's called, but you might have reason as an experimenter to have such an arrangement. This is all to say, right? You just have 2 pieces of metal, and the way you get to those pieces of metal tends to be along a thin wire. So it tends to be drawn with a wire going to each, but there is no wire between them because they are 2 separate conductors. So this parallel plate capacitor has a wire going into the back of one of them and the wire coming out of the other one. And then here, this third capacitor, capacitor C, has 2 wires going into the back sides like that. So these are different capacitor arrangements. And there is a generic diagram symbol for capacitors, and it's simply you just take 2 lines that are about the same length, and then you put 2 other lines. And it's meant to look like, right, this is the generic circuit symbol, diagram symbol. It sort of looks like the parallel plate capacitor. Yeah, so here is a capacitor. And in the future of this couple of lectures, the idea is I should be able to, well, yeah, so I'll get to that. So let me just stop there. Yeah, so I've got a circuit diagram symbol. We could say that this little thing is a 2 microfarad capacitor, right? So as an example, how much charge is separated over the 2 microfarad capacitor when it has a potential difference of, say, 5 volts, right? So remember that capacitance is charge separation divided by potential difference. So I've got 5 volts here, and I know the capacitance. And the question is how much charge? So let's solve. So Q equals C times potential difference. And the capacitance is 2 microfarads. And the potential difference is 5 volts. And this is, right, 10 microfarads times the volt. So this is 10 times 10 to the minus 6, because that's the micro. And then the farad, let's look at the definition of the farad from before. The farad is the coulomb per volt. So let's put in for the farad as just the coulomb per volt. And then don't forget that we still have to multiply by the volt. So the volts cancel, and we're left over with saying that the charge is a certain number of coulombs. It's 10 to the minus 5 coulombs. And that makes some sense. Like you could say that what the charge is actually 10 microcoulombs. Like that would be a simple way to say what the answer is, right? Okay,